Hey folks, today we're going to talk about fixed iteration looping. And our learning objectives are to create a loop for repeatedly executing a calculation when the number of iterations is known. And then the second thing we're going to do is we're going to use fixed iteration looping to animate a plot using the for-in loop format and the drawnow command. So loops are used to repeat a command or a series of commands over and over and over. And so there are two types of loops that we'll encounter. The first one is that when you're working through each element as an input to a calculation, and that's this case, because in this situation we would know the length of the array and we would know how many iterations you actually need to have in the loop. So this would be a fixed iteration loop. The second type is when you need to repeat a calculation until a conditional statement is met, and we'll deal with that later. And those are called the while loop or while break loops. So let's talk about the structure of the for-in loops. And so on your cheat sheet, you can see that we're going to have a for at the top and then an end at the bottom. So this is important to bracket the beginning and the end of the loops with these commands. And so the index variable, which we have, we're gonna change our index from some first value to some last value. Now the most common way to do this is to say for I, so index, we'll put an I there, for I is equal to, and then 1 colon, then the number you're going to. And the reason why is because we know that this colon operator, we have the first value, last value, and interval, but most of the time when using a for-in loop, we're going to be using integers. Now, as soon as we index something and we call it an I, then keep in mind that by doing this, we're overriding MATLAB's assignment of I to being an imaginary number. So if you have imaginary numbers in your series of commands or calculations, then make sure that you're using J for that, or that you're not using I for the index. You can choose whatever you'd like. So the common ones are I, J, K, M, and N. And so now you can have an interval on your indices as you're stepping through this matrix or stepping through these indexes. And that's uncommon, but just keep in mind that you can do this with your interval. Okay, so now the value of the index, or I, as you're looping through this for-in loop, isn't displayed while the loop executes. Now, it is possible to display the value, and you may want to do this for debugging. And the way to do that would just be to put I into your series of commands and don't add the semicolon operator that suppresses it. And then last, at the end of your loop, the index variable I is going to have the last value that it was assigned. So if you do for I is equal to 1 colon 10, then after the loop is over, I will be equal to 10. Now the best way to see this is really just to put it into practice. So if you open up your Calculate Factorial starter code, this will give you the skeleton for creating our own factorial calculation. And so we have our normal header here. We don't need any additional files. And so this script will use a sub function to calculate the factorial, and then we're going to check the solution. Now how we're going to execute that, as we're looking at our pseudocode, first we're going to calculate the factorial for the input value using a sub function factorial loop. Okay, our sub function factorial loop will be down here. And then at the end we want to calculate and display the error. So this is a new concept that we haven't talked about before, but we're going to define our error as our calculated factorial, which we're going to calculate using the sub function, and then we're going to subtract using the factorial built-in function to make our calculations. So we do have this factorial built-in function. Let's try it out. So if we say factorial of 5, then of course that's going to give us 5 times 4 times 3 times 2 times 1. And then that's 120. And so this is the MATLAB built-in function, and then we're just going to reproduce this with our own function, and let's see how accurate we can be. So in looking at our function, here's how we're going to call our custom function. We're calling the custom function a factorial loop, and so it's a sub function. And so recall that when making a sub function, we type in function. And then here is our format that we're using. So we're going to call this factorial value. And then factorial loop is the name of our function, and then we'll have input value. I'm going to change this to number. And so with any subfunction, make sure that you have an end here. And then it's always a good idea to put a header in your function so that you're telling the user what's going to go on inside the function. And so we've described this subfunction as its name, factorial loop, and this subfunction calculates the factorial of the input where number, the number input, is a positive integer. So pause the video for a moment and take, let's say 3 or 4 minutes, and then code this factorial loop subfunction. All right, so to code this, we know that we want to multiply, in our example, 5 times 4 times 3 times 2 times 1. And we would do that using a loop. And so in this case, always put your 4 in your end so that we know that we need to close it. And then it's 4, I is equal to 1 to the number that's coming in. So this is for positive integers that we're working with. We need to output a factorial value. Now inside of a loop, if we make the calculation factorial value, and we're doing this over and over and over, it's going to overwrite this each time. And so we know that we want to have the 1 times 2 times 3 times 4 times 5. And so we can say factorial value times I on each iteration. But that's only going to work if we make an initialization of factorial value as equal to 1. And so initialize to the unitary, and that's going to work because by starting our multiplication our iteration in our multiplication with I is equal to 1, if we initialize a factorial value as 1 and then we multiply it by 1, then that's going to work for our loop from 1 to 1, and that would be 1 factorial. And so then if number is equal to 2, then it's going to loop through 2 times, and it's going to be factorial value is equal to 1, and then as it loops through, it'll be 1 times 1, and then on the next value, it'll be 1 times 2. And so hopefully you can see how that iterates. Please play around with that to make sure that it works. Always recommend putting in comments, which we will call pseudocode later, that are saying what each of these steps are. And so the first step that we had was to initialize a factorial to a unitary number. And then the second step was to find the product of the integer series. And so in this product, we've executed the for end loop, and we know the number of iterations that we want to do. It's the number of indices, and we've always closed it with an end statement. So let's see if this works. We're going to try the input value of 7. We're going to call the subfunction factorial loop with that same input value, and then let it give us our error. Hopefully our error should be equal to 0. So our calculated factorial was 5040, and our error is 0. We can put this in. We can try different values here. Let's try 5, which we had mentioned earlier. Don't forget to save it. Run your code, and 120. So this is working out pretty well. So a question arises here. What if we give it the factorial of 0? So 0 factorial is equal to 1, which would be an edge case here. Well, it happens here. Let's try it out. So our input value being 0. And in this case, it did give us the calculated factorial is equal to 1, and so the error is 0. Now this is one of those instances where this worked out such that we gave it number is equal to 0, or our value, forgive me, what did we call it? The input value is equal to 0. So it came into our function as a 0, and then it looped from 1 to 0. Now, so I is equal to 1, then I is equal to 0. And as we move through this, just given the logic, it looped through 1 time. And so the factorial value was already equal to 1, and it was a 1 times 1. And then when it did the 0 loop as it went through, it didn't make the calculation. So in this case, we didn't need to control for the edge case with any defensive programming, which we'll deal with in the future, which is going to be based on conditional logic. Now for the second learning objective that we have today, we wanted to animate a plot using a for-end loop format and then use the drawnow command. And so this is one great application of using a for-end loop is when you want to visualize something. And so my work is typically in dynamic systems. I want to see how the system and the mathematics evolves over time. So often when I animate a system, particularly in human movement, I'll have time in my loop, and I'll loop through and I'll draw each time to look at how the motion of the system looks at each time. And that can be, you want to evaluate the mathematics, you want to evaluate something that you're drawing. So you can see this command here in this format. We're going to use our for loop. For is I is equal to first value to last value, end, and then we'll be putting in this drawnow command. So pull up your animation cosine example starter code, and you'll see here that we have our normal things in our header, and it's a script that animates the cosine function. This is a function that we all know. We're going to plot it and animate it using blue diamonds across a specified domain and a number of points. And so in our pseudocode, we're going to create the domain and the values of the cosine function. So go ahead and make that calculation before you do your animation. I always think that's a good idea. Your animation can be tagged onto the bottom after you've done the mathematics. And so we want to create our cosine function from 0 to 3 pi, and we want to use 100 points across this. And so after our number of points, we need to create an x domain. And so for our x domain, we'll use the linspace command. And linspace from xmin to xmax, and then we're going to use 100 points, which would be the number of points. So you can always alter the number of points that you use in your domain. So we want to suppress that output with a semicolon, and then we want to calculate our cosine. So cosine value is equal to cos, and then inputting our x domain. All right, so if we get back to our cheat sheet and look at our format here, it's going to be for and end, so always for and end, and then index, and we'll have our series of commands. And in our series of commands, these are going to be plot commands. So animate the cosine function. Let's do for end, and I is equal to 1 times the domain itself, or to the length of the domain. And so we use the built-in function length of the x domain. And then what we want to do is we want to plot the x domain by the cosine value. We want to make those blue diamonds, and so that'll be BD for blue diamonds. And then as we're doing our plotting, remember we're looping through, so anytime that you have a loop, we want to be doing something with this index I. And so to plot each diamond 1 point at a time, we want to plot just the first, when I is equal to 1, we want 0, which is the first part of the x domain, and then we want to plot it against the point of the cosine value at that same index. Okay, so if we run this, we'll see that we get a single point. And it raises the question, why did we get a single point in this case? Well, let's investigate this. So the single point that we have is at, let's do our grid on so we can see this a little bit better. And we can see that our single point is located just below 9.5. So it's between 9 and 9.5 in the x-axis, and then it's equal to -1 on the y-axis. And so what this is telling us is that it didn't plot just the first point, but what it did is it plotted just only the last point. And so, what we had here is we've got a phenomenon in which it plotted the first point and then replaced it with the second point, replaced it with the third point, and so forth until we got through all 100 points. So what we missed here is that we need to do a hold on command. So let's run it here and see what happens. Okay, all right, so with our hold on command, we see that we get the entire cosine. Okay, but we still didn't get our animation. Our animation that we want is for it to start at 1 and to draw each of these points until we move all the way to the very end of our X domain. And so let me put that grid on, back in. And then, so this is where our draw now comes in. So draw now is saying, hey, take a pause and then draw each of these points. So let's try it again. Whoops. This needs to be draw now with no space. All right, let's go back. There we go. And so now we've animated our cosine, and it drew each of these points with a small pause. Now, you can investigate the draw now command in your help menu and understand how to time the reiterations of the drawing. Now, one of the things that we can still improve on this is that, you know, when it drew our function, our cosine function, it expanded the horizontal window and expanded the vertical window as it went. So let's go ahead and set those so that our window is clearly on the right limitations, so xlim and ylim to begin with. And so we used xmin and xmax. So it's going to be xlim, xmin, xmax. And then for ylim, so our y limits of our plot, then let's use the minimum of the cosine value. So min of our cosine value, because we've already calculated that outside of the function, and take that all the way up to the x max. Okay, this should do it. Oh, whoops, I did the wrong thing here. This needs to be the cosine value, not our x max, x min. Let's try that again. Ah, much better. It goes from -1 to 1. Okay, so explore using this draw now command within a fixed iteration loop. I think you'll find that helpful when visualizing the systems that you'll be studying in the future. I want to make one other comment here, and that's on how do you choose the number of points. Now, when we drew this with 100 points, it worked out nicely. We could see that cosine evolving as it needed to. But if we reduce the number of points, let's say it's 50. So there's an advantage. It's going to draw a little faster, and we start to get these spacing between the values. But as we reduce this number, okay, still looks like a cosine, we're going to see that the cosine itself is going to look less and less like a cosine. So if we only use 10 points, it's getting a little bit speculative, and let's say we get down to 5 points. All right, and you can see that we've really lost the features of our cosine. And so this is a feature that you'll run into in signals and systems and some other classes, in which when you reduce the resolution, we get a phenomenon called aliasing, in which there is a cosine that's driving this function, but we can't see it. So it's something to protect against. And so to do that, you're going to increase the number of your points. And let's say we do 300, let's just to be safe. Of course, the trade-off is that we get, with high resolution or high sampling rate, is that everything becomes slower. We end up taking up more memory. And so you're going to have to find that happy medium when you start doing experimental analysis in signals and systems.